One way we can show that W is a subspace is by showing that W can be represented as a span of a set of vectors. So if I take A here and say, and let's just solve it for A. So A would equal 3B plus C. So let's substitute that in. So A, B, C turns into 3B plus C, a B and a C. And then that's the same thing as saying take the constant, or the scalar B, multiply it by 3, 1, 0, and C, 1, 0, 1. So I can say that this W is the span of the two vectors, 1, 0, 1, like that. And that does say that it is a subspace. So what's the other way we show it's a subspace? We show that this vector here, these vectors can be satisfy the three criteria, so that there is a zero vector. And so since I can let A and B and C equal 0, that gives me the 0 vector. I'm good. Number 2 would be this closed under addition. So that means if I have two things that satisfy this, so if I have an A, B, and a C, and then plus a D, E, and an F, and in the same way that A has this relationship, my D would have this relationship, right? And so when I add them together, it would be the same. So I would get D is equal to 3E plus F. So if I just replace this with the A equaling 3B plus C, BC plus 3E plus F, EF, this will look the same as 3B plus C plus 3E plus F, B plus E, and C plus F. So it is the correct form. Remember, we're always trying to match the form. And then it would be closed under scalar multiplication also, because if I took any k, any real number, and I multiplied it, multiplied my A, B, C, then I would still get a Ka, Kb, Kc, and this relationship here would still stand if multiplied by k. So we can obviously see this is the easier way. So anytime I can write a set and try to show that it is a subspace, breaking it up into a span of a set of vectors is absolutely the easiest way. So these ones I didn't have solutions for either. So again, oh, look at that. I think I can factor out a t. So I get a 3, 1, 0. So I can say yes, a subspace, because I can write it as the span of this one vector. So yes, it's a subspace. How about this one? If I factor out a t, I get a 3, a 0, and a 1, and I'd have to add on that constant. So no, cannot be written as a span of a set of vectors. Or I could say there's no zero vector, right? We say no zero vector because I could let t equal 0, but that still gives me a 0, 2, 0, and that's not the 0 guy. Now about this one. Yes, it is a subspace of R3 because I can factor the t out. And so I can say that, yes, this set is the span of this one vector. And, because I should label this number 12, how about this one? I can factor the s out, and then I can factor the t out. And I can say, yes, it's a subspace because this set will be the span of these two vectors.